Hello, everyone. I'm Yiyuan Zhang, presenting UniRepLKNet, a universal perception large-kernel ConvNet for audio, video, point cloud, time series, and image recognition. This work is in collaboration with Tencent AI Lab and the Chinese University of Hong Kong. Our key finding is that large-kernel CNNs can be more powerful than initially thought, even in areas where transformers excel. Thank you for joining, and let's dive into our research. Moving on to our first contribution, we developed 4 guidelines specifically for large-kernel CNN architecture design, resulting in a powerful backbone called UniRepLKNet. With only ImageNet 22K pre-training, UniRepLKNet achieves state-of-the-art performance, boasting 88% accuracy on ImageNet, 56.4 box AP on COCO, and 55.6 MIOU on ADE 20K. These tables highlight our model's superior accuracy and efficiency compared to other leading methods. Our approach includes 4 key architectural guidelines for large-kernel ConvNets. The first is the local structure design. We use efficient structures like SE or bottleneck layers to increase depth and improve performance. And the second guideline is on reparameterization. We utilize dilated convolutions to capture sparse features. This includes a submodule called the dilated reparam block, which contains parallel dilated convolutions alongside large kernel convolutions. This block can be transformed into an equivalent large kernel convolution, as illustrated in the figure below. The top row shows the structure perspective with sequential dilated convolutions, 9 times 9, 5 times 5, and 3 times 3, with varying dilation rates integrated with batch normalization. The bottom row demonstrates the parameter perspective, where the reparameterization process transforms parallel dilated convolutions into an equivalent large kernel convolution, effectively combining the benefits of both approaches. These innovations help us optimize both the structure and parameter space of our models. Continuing with our architectural guidelines, we have the third guideline on kernel sizes. It is important to choose the kernel size based on the specific downstream task and the adopted framework. For example, in the case of the UperNet for semantic segmentation tasks, using large kernels too early in lower-level layers might produce negative effects. However, this does not mean that large kernels will reduce the model's representational capacity or the quality of the final features. Last but not least, the scaling law of large kernel ConvNets. For a small model that already uses many large kernels, when we increase the model's depth, such as from 18 layers of a tiny level model to 36 layers of a base level model, we should add depth-wise 3 convolutions instead of increasing the large kernels. This is because the receptive field is already large enough. Nonetheless, using such efficient operations to enhance feature abstraction is always beneficial. On the right, Figure 1 illustrates the architectural design of UniRepLKNet. It shows a large kernel, LarK block, which includes the dilated reparam block we proposed in this paper, an SE block, a feed-forward network, and batch normalization layers. The key difference between a small kernel, SMK block, and a LarK block is that the LarK block uses a depth-wise 3 times 3 convolution layer instead of the dilated reparam block. Stages are connected by downsampling blocks implemented by Stride 2, dense 3 times 3 convolutions. Our second major contribution is the development of extremely simple multimodal solutions with UniRepLKNet, achieving state-of-the-art performance. In our pursuit of simplicity and universality, we do not make any changes to the main structure of the UniRepLKNet model when applying it to other modalities. All experiments use UniRepLKNet small. Instead, we process video, audio, point cloud, and temporal data into C times H times W embedding maps, just as we represent images as 3 times H times W tensors. For example, we treat the spectrogram of audio as a single-channel image, where C equals 1 H equals T and W equals F. We project point clouds into 3 views to get 3 single-channel images, making C equal 3, while H and W can be arbitrarily specified. We simply concatenate frames in a video to get a large image. For instance, a 16-frame 3x224x224 video is concatenated to form a 3x896x896 input. For temporal data, we borrow the embedding layer from CoreFormer to convert the data into tensors in the hidden space and then reshape it into a single-channel image. This approach allows us to maintain a unified and straightforward method for processing various data types. Now, let's discuss the performance of UniRepLKNet across different modalities, including audio, point cloud, and video. UniRepLKNet demonstrates significant speed advantages and achieves state-of-the-art levels in time series forecasting tasks such as global temperature and wind speed forecasting. Additionally, it performs at or near state-of-the-art levels in point cloud, audio, and video tasks using extremely simple pre-processing methods and an unchanged model structure. For audio recognition on the Speech Commands V2 dataset, UniRepLKNet-Small achieves an impressive accuracy of 98.5%, as shown in Table 10. In point cloud analysis on the ModelNet 40 dataset, UniRepLKNet-Small reaches 90.3% mean accuracy and 93.2% overall accuracy, as indicated in Table 12. For video recognition on the Kinetics 400 dataset, UniRepLKNet-Small achieves 54.8% accuracy, as seen in Table 11. Despite the lower performance in video recognition compared to other tasks, our model's simplicity and universality across modalities are noteworthy. These results highlight UniRepLKNet's versatility and efficiency in handling diverse data types with minimal changes to the model structure. To test UniRepLKNet's capacity to handle temporal data, we took on a massive nature-level task, global temperature and wind speed forecasting. Despite UniRepLKNet originally being designed for image-oriented tasks, it managed to surpass CoreFormer, which was specifically designed for this task and was the previous state-of-the-art. This finding is particularly intriguing, as large-scale time series forecasting tasks typically seem more suited to LSTMs, GNNs, and transformers. The success of our CNN in this area is similar to the success transformers achieved when they were imported from NLP to CV. Our minimalist approach to audio, video, and point cloud tasks also works astonishingly well. For more details, please refer to the paper. As shown in Table 9, UniRepLKNet delivers new state-of-the-art performance in mean squared error and mean absolute error for both global temperature and wind speed forecasting. This performance solidifies UniRepLKNet's versatility and efficiency across various data types and tasks. Thanks for your attention. If you're interested in exploring our work further, all the code, models, and reproducible training scripts are available at our GitHub repository. You can access it directly by visiting the link or by scanning the QR code on the slide. We encourage you to use our code and models for your own research and projects. Feel free to reach out if you have any questions or need further assistance. Thank you.